Thank you, the organizers, for inviting me here. I would like to tell you something about a system where we have a nice degeneracy in energy between magnetic anisotropy, corner screening, and exchange interactions. And since it seems to be a good fashion, I will continue with iron atoms. And we put them on platinum surface. So the outline of my talk will be these three major topics, where the first two belong together. And I would like to show you how we can tune magnetic properties of single iron Hund's impurities by hydrogenation, and then use these species to trace exchange interactions, like it was already shown a little bit by Professor Wiesendanger. And in the end, I will also address the question if maybe 4F atoms are a nice quantum bit. So let's start with the first part. What is a Hund's impurity? When you consider an iron atom put on a surface, then you have different energetic contributions that create various electronic states, and you can use a 5-orbital Anderson model to describe these states. And if you have a different number of electrons in these orbitals, the...
Can you speak up a little bit, or put the microphone on?
Oh, the microphone, sorry. Does it work? I hope so. Sorry for that. Then we have the Coulomb interaction that basically separates the states. And if you want to now flip one of these electrons, then you have to pay Hund's energy to, for example, put it from the up state to the down state. So the Hund's rules actually tell you how to arrange your electrons in the orbitals. And this is where the name of the Hund's impurity is coming from the famous German physicist. But you still don't know what it is. Of course, you have to do this for all the states you can occupy, and there are various more configurations possible. And when you zoom in into this configuration, which is the 3D6 configuration for iron, then you will see that there was more separation in the states by crystal field and spin-orbit coupling, and you get new hybridized orbitals, which then split the states here. And you can also then have hybridization between the atom and the substrate, and this leads, when you have a small Coulomb energy, which is the case in our system, to large charge fluctuations between these states. So this large charge fluctuations then can lead, or will lead, to a mixed valency, which leads to a spin which is not integer or half integer anymore. And for our system, you will see it will be something like approximately 5 halves. And this means that we have a strong hybridization with a substrate where the hybridization is larger than the Coulomb energy, but not big enough to overcome the Hund's exchange. And this leads to the second need, which is necessary to form a Hund's impurity, which is maintained magnetic moment, which is then stabilized by intraatomic Hund's exchange. So with these two necessities, we end up with a Hund's impurity, which is basically the smallest picture of a Hund's metal, which is important to explain several physics. So first, let me explain you now what happens when we put iron atoms on a platinum surface. You can see an overview STM image here. The iron atoms were cold deposited at roughly 4 Kelvin, 1% of a monolayer, and we can obtain two different adsorption sites, namely FCC and HTP, which you can see in the lattice here, where these three triangular atoms only are a reference for you. And when we are lazy enough and just wait, then we will end up having hydrogen in our chamber, and the hydrogen can attach to the iron atoms, and to FCC and HTP, there can be 1 or 2 hydrogen atoms, and you can see this directly in the apparent height, which is changing from 100 to 180 picometers. So we end up in total with having 6 different species on our system, and similar observations have already been done in the group of Harald Bune and also by Markus Ternes. And we can then also place our STM tip above these hydrogenated atoms, apply a voltage pulse of something like 500 millivolts, and remove the hydrogen to end up with a bare and clean iron atom again. Then we wanted to find out the magnetic moment of these species, and Sami Lunis' group in Jülich performed KKR calculations. And since platinum is a highly polarizable metal, you need to include a huge number of platinum atoms in the calculation, and you see that the orbital moment is nearly quenched, and we end up with a total magnetic moment of roughly 4.7 for the two species. From this we can estimate the effective spin of the system, which is iron plus platinum, to be 5/2, and put this in our effective spin Hamiltonian to model some data. And you just have to believe me, I won't show this in detail now. When we perform the calculations for the hydrogenated complexes, which was done by Sascha Lichtenstein's group, then we see that the magnetic moment stays nearly unchanged for these species. And with this we can look into the two needs we want to have to obtain a Hund's impurity, which was done by calculating hybridization functions in quantum Monte Carlo calculations. So first of all, we need this metallic behavior of our occupancy, and you can see here when we drive the hybridization to the limit of Coulomb interaction that we end up with a smeared out continuous line for the hydrogen and for the iron and hydrogenated iron complexes instead of this atomic like behavior. And secondly, we still need to obtain this magnetic moment I've shown you, and for this you can do a calculation of the self-energy compared to the Matsubara frequency. And in this case, we have to believe the theorists that they say when here we obtain still, the curve does not go through zero for low Matsubara frequencies, then we still have scattering of the substrate electrons with a magnetic moment. And this is what proves that we still have a magnetic moment, although we have strong charge fluctuations, and we have all of these 6 complexes which we obtain are Hund's impurities. But what exactly does the hydrogen do now? For this to find out, we performed inelastic scanning tunneling spectroscopy. All our measurements are done at 0.3 Kelvin. And for the FCC case, we see a spin excitation step at 0.75 millielectron volts. And for HCP, a spin excitation which is much smaller in energy at 0.90 millielectron volts. And also, you will see that the line width here is much sharper than it is for the FCC case. We then attach one hydrogen atom, and we'll see that the intensity for the FCC case becomes much larger, and also it shifts to higher energies. And for the HCP case, we see it even decrease in energy, and you can maybe already see some kind of peakiness here. And when we put a second hydrogen atom attached to it, then we find that there is even a conv resonance. So we directly observe that the hydrogen can affect the magnetic properties, which has also already shown by Harald Bune, where they have shown that the spin can change for cobalt atoms with hydrogen. And we performed then measurements for the species in a magnetic field and plot the step excitation energy you see here versus the magnetic field. So basically this gives you a hint of the anisotropy, and you see for the FCC case our magnetic field is aligned perpendicular to the surface, that we have just a linear Siemens splitting for all the 3 iron and iron hydrogen species. And this means that the anisotropy constant D is becoming more negative in value, so we have a stronger easy axis here, and the states get separated even more, and we have a ground state of Jz plus minus 5/2. For the HCP case, you can see this color plot here where now the colors represent the ISTS signal intensity, and at roughly 3.5 Tesla, you see that there is a turning point of this magnetization, which is rotated from an in-plane to an out-of-plane direction with a magnetic field. And this means we have an easy plane system here, and the ground state of the system is a plus minus 1/2 state. Performing these measurements with hydrogen or two hydrogen attached shows you that the anisotropy is decreasing, the states come more closer together, and here we have this condor resonance, which you have already seen. And what you will see here is that the states here are really very close together and are barely separated. So this already gives us a first hint that we might have a multi-orbital condor effect here. Then we perform temperature and magnetic field dependent measurements, which you always have to do when you want to prove you have a condor effect, and fitted these spectra with rota function and with a Anderson-Applebaum model. And I don't want to go into those details here, but we then use Wilson's definition to define a condor temperature and find that the condor temperature is something like 2.8 Kelvin. And this condor temperature actually is much larger than the anisotropy splitting of our two states, 1/2 and 3/2, which is only roughly 100 microelectron volts. Additionally, we can plot the peak splitting we obtain from these measurements and also the G factor, and we will see that we will get huge differences from a spin 1/2 model, where this would be this line here, or we would have a G factor of 2. And all this leads to the conclusion that we really have a multi-orbital condor effect, where not only spin 1/2 orbital is involved, and this might be a test system to develop more advanced condor theories to apply to this model. And this condor resonance is actually very sensitive, and we want now try to use it as a sensor. And this brings me to the second part of my talk. And you see here on the left side the condor species, and on the right side the iron atom, which is now always green or red respectively. And unperturbed case, we see the condor resonance and the sharp iron excitation. When we bring them closer together here at a distance of 3 lattice sites, we find a huge splitting of the condor resonance of roughly 500 microelectron volts, and also the excitation on the iron atom shows a shift to larger energies. And these measurements we performed for different pairs of different distances. You can see some distinct lattice sites here, and you see that the splitting first is very huge, and then it nearly vanishes, and we only get a drop in intensity until we have an unperturbed condor resonance here. And for larger distances, which is this atom here, we even see there is a drop in intensity again, so maybe there is some kind of oscillatory behavior. And then we went ahead and modeled all our data, and we took more data of all these different pairs we can obtain in a magnetic field, and model it with a local spin Hamiltonian with a Zeeman energy and anisotropy only in the lowest order here. And you see Heisenberg exchange and Dialoghinsky-Moria interaction. I have to point out that we are only sensitive to the absolute value of the Dialoghinsky-Moria interaction, and only the perpendicular component, which in our case means the perpendicular component on this line connecting the two spins in plane. And we did this by the very nice model Markus Ternes has provided for us, and as an approximation we used constants we get from uncoupled species. So we only change the Heisenberg and the Dialoghinsky-Moria interaction to fit our data. And this is what I want to show you at this example for the 3 lattice sites again, where you can see in the color plot that the condor resonance splits, and the iron HEP atom does not show this turning point of the magnetization anymore, which you can remind yourself of from this level diagram. So there must be something, some exchange interaction going on. And by modeling this only with a Heisenberg term, we cannot find a good fit for our experimental results. So also the conv resonance is still shows a different splitting, and you still see this magnetic turning point of the magnetization. So we have to include Dzielottinsky-Mourier interaction roughly in the same order of magnitude like the Heisenberg exchange to model our data. And this we have then done for all the several pairs we have built. On top you will you now see the Heisenberg exchange, and below Dzielottinsky-Mourier exchange. And you can compare the blue data points with the theory, which are HTP-HTP pairs, and we will see that it fits quite okay, with maybe some 2 points that deviate a little bit. And for the Dzielottinsky-Mourier interaction, we can nicely follow the theory, showing this oscillatory behavior. When we only plot the theoretical values, then you will see that we have positive and negative sign of the Dzielottinsky-Mourier vector. And you also see that we cannot completely neglect the dz component for those two distances, which might lead to the different experimental and theoretical values we have seen before. And when you look at only these 3 dots here, you can see it changing from positive to negative to positive, and this leads to a different sense of rotation between the two spins, leading to a positive or negative chirality. And in the video below, you will see the spin excitation value for those 3 pairs, and you will see they have different sense of rotation from left to right in the pairs here.
What are the axes here? It looks like small.
Oh, sorry, it's the expectation value in z direction and the parallel component.
For the two spins?
Yes. You can also try to get some kind of feeling for what is a classicalness for the system when you calculate the mutual information from the von Neumann entropy. And this means that for zero mutual information, our variables are completely independent and behave classically, and we can have high mutual information, which makes them more like a quantum mechanical system. And this was calculated actually by Markus Ternes. And you see that when you switch on in the red curve the Dzielottinsky-Mourier interaction, the system goes much faster into this classical regime. So also dm drives the system much faster into a classical spin. Okay, with this I would like to come to the last part of my talk, concerning holmium 4f atoms also on a platinum 111 surface. And the question is how we can reach our ultimate goal to form single spins to use as data storage or processing devices, like we have more, maybe obtained by 5 atoms clusters or the logic device. And using rare earth atoms are maybe a good idea because they have a strongly localized 4f states, which are very closely bound to the nucleus and far away from interaction with a substrate, which is done maybe by mainly by the other states here. So there have been 2 recent publications about this topic, one from the group of Wolf-Wolfhekel, which is an STM work and showed a stable magnetic ground state with a lifetime of several minutes. And then there have been XMCD measurements by the group of Harald Brune, where they measure a different ground state. So we want to address the question if we can even detect 4f magnetism with an STM and how it interacts with magnetic impurities, and if we can see a stable magnetic ground state. So firstly, as I already said, 2 different ground states have been reported in the paper of Miyamachi et al. The ground state was derived from DFT calculations with a Jz equals 8, leading you to this parabola of the states here, and spin excitations have been measured for FCC and HTP of 8 and 5 millielectron volts, and this ground state you have seen in the telegraph noise supposed to be protected by symmetry arguments. If you look in the work of Harald Brune and co-workers, then you will find that they have performed XMCD and multiplet calculations like you have just learned in the talks before, and obtained ground state from Jz equals 6 in this case, then directly from experiment. And then this Jz equals 6 is this mixed state here, which has the lowest energy then, and the outer states even go up in energy again. And the zero field splitting would be something like 4 microelectron volts. So maybe we can see some of these excitations here. And for this, we arranged holmium and iron atoms close by, because we know the iron system very well, and measure it with the same tip simultaneously, or right after another. And we can easily reproduce our data for iron HCP and iron FCC, which is indicated by the dashed lines. And when we do the same measurements on holmium, we do not see any spin excitation at these reported values you have seen before. We have performed these measurements in first and second derivative measurements and with a various number of parameters, and cannot find a spin excitation signal. So maybe the 4F shell is not accessible. The question is still if it,
There's wiggle at around 4 million.
Yeah.
Is that something?
No, it's not here. So it also would have to be on the left side. And this is only one spectra now. I won't show you all the spectra we have, but this is nothing. But the question is still if it does interact magnetically. And for this, we actually did the same measurements like with the conv resonance. So we manipulate holmium and iron atoms at various distances. The closest proximity is here 4.24 angstrom, and measure all the different distances for iron atom now and holmium atoms. And for the largest separation of roughly 14 angstrom, we find an unperturbed spin excitation, which is represented in this color plot. And on the holmium atom, we cannot find any feature. When we then do the measurements for all the pairs, we see that there is no change in the iron excitation at all. It's always at the same energy. Only for maybe the closest distance pair, we find that the intensity drops in the direct exchange regime, but the energy of the excitation is still the same. So we do not see any RKKY interaction coming from the holmium atoms, and from theory we know that also the holmium atoms only very weakly hybridize and polarize the platinum substrate from the 4F states. Still, we tried to perform spin polarized measurement and try to find the switching which have been reported of this stable magnetic ground state. And for this, we built iron 3 clusters as a reference, which you can see here, with an apparent height of roughly 200 picometers, and then picked up some iron atoms to add it to our chromium tip to really get a spin polarized tip, and measure telegraph noise, as we have already seen in some talks, and as we have shown for the iron 5 cluster on copper 111, and perform the same measurements with the same tip and on the holmium atom, and we see that there is no switching at all. And we performed the measurements, of course, not only on a time scale of 50 seconds, but went up to several minutes and performed various parameters measurements and cannot find a switching signal here. So either we have a paramagnetic behavior of the holmium, or the spin polarization is too weak to be detected by us. So we do not observe magnetic feature of holmium atoms at all with our STM. So maybe we cannot access the 4F shell, and the coupling, the intraatomic coupling from the 4F to the 5D shells is very ineffective. And for me, I think it might be still a good strategy, as we have already seen these many symmetry arguments, to find symmetry effects that protect the spin. And with this, I would like probably to skip the summary, because you already remembered everything of this, and just thank all the people that are involved, of course, Professor Wiesendanger, and also Alex Kajitorians and Jens Wiebe, who are doing great work. A former member working on the iron system is Tobias Schlenk, and my colleagues in the lab now are Andreas Sonntag and Jan Hemenau. I'd like to thank Markus for providing this nice model, and theory calculations have been done by the group of Sascha Lichtenstein, also by Tim Wehling, and by the group of Sami Lunis. And with this, I would like to thank you for your attention.